Hello, so today we are doing this problem called generate parentheses, and the problem says that we get n pairs of parentheses and we're going to write a function to generate all the combinations of well-formed parentheses using this that n number. So for example, if we get n equal to 3, that means we need to form all the different combinations of valid parentheses such that we have 3 open parentheses and 3 closed. So this here, for example, we have 3 open, 3 closed, and so we have valid parentheses combination here. And same thing for this one, and this one, and these are the only ones we can construct that are valid using 3 open and 3 closed. And so that's the problem. Now let's think about how can we solve it. Okay, so now that we've seen the definition of the problem, let's just look at how we can solve it. So here I have just a couple of examples that I've drawn out. So when n equal to 1, we can use only 1 open parentheses and 1 closed. And so here we have this one for n equal to 1. For n equal to 2, we can have 2, and so the 2 forms possible that are valid are this one and this one. And for n equal to 3, we have these here. And maybe more, but yeah, you get the idea of what we are being asked here. So how can we solve this problem? So the first thing that can come to mind is a couple of requirements that have to happen for our parentheses to be valid, right? So let's just write these down. So requirements or observations or whatever. And so those are that one, we should not start with a closed parentheses, because if we start with a closed parentheses, right, like this, then we pretty much can't do anything. If we put an open parentheses, that won't make it valid. So if we start out with a closed parentheses, that just makes the problem, that makes the parentheses will not be valid no matter what we do, right? And so our first constraint here is that should not start with a closed parentheses. Another requirement that we need is that the number at all times, the number of open parentheses should be bigger or equal to the number of closed parentheses. Why is that? So let's take an example where that's not the case. Let's take the example of, let's say I have a number of the open bigger than the number of closed ones. So that would mean, smaller, which is the reverse of this inequality here. And so if I have that, what would happen in that case? So I would have 2 here, and then I would have 3 closed. So here I can't get a valid parentheses no matter what I add, because I can't add I can't add an open parentheses at the beginning to make it valid, and so I'm stuck here. So because having this makes it invalid, we don't, so basically, to clarify this requirements here, so this is requirements for valid parentheses or valid expression. So now that now also another condition that we want is that the number of open parentheses have to be less than or equal to n at all times, right? Because that's what the problem says. We want to have only n pairs, and so we need only n open parentheses. Also, an adjacent to that or similar to that, we should have only the number of closed less than or equal to n. But this is already happening because of inequality number 2. Since we can't have the number of open parentheses be bigger than n, and since that already puts the constraint on the number of closed parentheses to not be bigger than n, right? And so these are the minimum things that we need to that we need to happen. And so one way we can think about solving this problem is using recursion here, because you can see the structure of the input that we have is, it's very recursive, because if we find for n equal to let's pick here 1 2 3, n equal to 3, we can find a part of that is n equal to 4, right? We just need to have this one. And the same thing if we had like this and we add this, so this is for n equal to 2. But if we have this n equal to 1, we can just add an open parenthesis and closed parenthesis. So this immediately gives us the idea that we can solve this with recursion. And so now let's think about what can our recursion look like. So we can have a function that gets passed both the number of, let's call it helper function, that gets passed the number of open parentheses, let's call them open. These are the parameters that we are interested in, because we wanna make this condition valid, and we want to make this one valid and this one valid. And so we need to know the number of open and the number of closed to be able to tell, right? And so for that, let me just write the code with something different. Let's pick, I don't know, let's pick this one. It's good enough. So our helper function would have to have open and close, so that we can verify 2 and 3, for example. And we need to know also the string that we formed so far, like the partial string that we formed so far, so that we can append the open and the close parentheses to it, and so that at the end we can add it to the result, right? And so this would be our function, and we need to have a base case since it's a recursion. So we need to have, for recursion, we need to have a couple of things. We need to have we need our base case, and we need like subproblem or smaller state, right? Recurs on smaller state. And we need the operation that will combine the problems, right, or the solutions. And so what is our base case here? So our base case in this here is that when open and closed, we already have n of them, because we are done at that point, right? And so so our base case is when open is equal, the number of open parentheses is equal to the number of closed parentheses, and both are equal to n, right? And so at that point, what should we return? At that point, we should just append to the result. We should just add the string that we formed using these open and closed parentheses to the result, right? Now, what is our subproblem, and how can we recurse, right? We have two things we can do, right? We can either add an open parenthesis or add a closed parenthesis, right? And so the different things that we can do, if we are adding an open parenthesis, then we will increase the number of open because we just added one, so +1. The number of closed stay the same, and we will need to add an open parenthesis to our string, because that's what we are doing here, right? And for the adding a closed parenthesis, we need to have helper open stays the same, and since we are adding a closed parenthesis, this one becomes 1, and since we are adding a closed parenthesis, we'll do that. But we need to be careful here, because we have some requirements here to handle. We should not recurse if these parameters, these requirements, one of them is not happening, because otherwise we would not have a valid expression. And so for this one, what is the requirement? For this one, we want the number of open parentheses to be less than n, right? Because of 3, right? So this one here, we should do it only if the number of open parentheses is less than n. Because if they are equal to n, that's the base case, and the rest is less than n, and so this is because of 3, the requirement number 3. What about the closed parentheses? So the closed parentheses, we have requirement number 2 that state that the number of closed should be always less than the number of, or equal than the number of open. And we already handled the equal case in the base case, so now we need to do that call only if the number of the number of closed is less than the number of open. And so this should happen only if the number of closed is less than the number of open, and this is because of requirement number 2. And so now we know what recursion calls we should do, and then the operation is just like we already done that. Our operation is concatenating the string, and so pretty much we are done here. We know our recursion, we know our base case, and so we can just plug that in here. And so that would mean if the open is equal to the number of open is equal to the number of closed, then we need to have our result, and we need to add the string we formed so far, and then after that we can start doing our recursion operation that we mentioned here. So if open is less than n, we can just do this call here, and if close is less than open, then we can do this call here. And that's pretty much it. And the function here, we will call it by passing zeros for open, and passing 0 for close, because we haven't done anything initially, and opens an empty string. And then at the end we can just return this result that we will have initialized beforehand, and we kept adding to it all the valid expressions, and at the end we can return that. So that's pretty much the solution for this problem. Now let's code it up and submit and see if it works. Okay, so now let's implement the solution that we just went through in the explanation. And so what needs to happen here is that we need to have a helper function that has the number of open parentheses, the number of closed. Python opened is a keyword, so opened, closed, and s. And so we do our base case, which is if opened is equal to n and closed is equal to n. We add to the result s, and then we return. We are done. We just need to create a result array here, and then here we do the condition that we set for the requirement for the open parentheses, which is less than n. We call helper with, since we will be adding an open parentheses, +1, and a closed stays the same, and we add the open parentheses. And then for adding closed parentheses recursion, the condition is that open needs to be bigger than closed, right? Or closed needs to be smaller than opened. And so to do that, and then closed we added 1, and opened stayed the same. And at the end, we can just call the helper function here with 0, since we haven't added anything, and an empty string. And at the end, after that, we return result, because they will have been added in this result array here. Okay, so that's the solution to this problem. Now let's run this and see if it passes. Okay, looks good, I think. I'll submit. Okay, so that solution passes. In terms of time complexity for this solution, we do 2 calls here. We branch 2 times in. If you kind of draw the tree that represents this solution, we branch 2 times every time, and we go through this for every combination n times. So overall, it's around O of 2 to the power of n. So it's n. So it's very expensive in terms of time complexity, but it still passes here. So can we do better than this, or can we at least solve it differently? So we can do. There is another solution where we can do this. So here we did it by decomposing with adding the open and then closed parentheses. But we can do it in a different way that I will explain right now. Okay, so now let's see how we can solve this problem differently. So the first thing we need is, there is this observation here. So if we just draw out n equal to 2 again, so n equal to 2 is the following. We have this one, and then we have this one. Right? And n equal to 3 is the following. We have open 3 times, open, closed. We have this one, and then we have this one, and we have this one, and then we have the fully this one. So these are the combination for n equal to 3. So one observation that we can make here is that we can decompose n equal to 3 here into the following format, right? Which is, we can have it be an open parentheses with something here, and then one open and closed, or actually maybe and then another expression here that we don't know. It may be empty, it may be something else, and so we can call whatever we will put inside there, let's call here x, and this one y. And so if this expression here, you can see for the first case, this case, the x expression is just this part here, and x is empty, so x is empty in here, and the y is this portion here, and y also can be decomposed into the same structure. Same thing with if we take the other case, let's say if I take this one, you can see this is x, this is the x inside these parentheses is empty, and y is this portion. If we take the other example, which is this one, so you can see this is the portion that has the x, and x is this inner one here, and y is this one. So you can see every string can be decomposed, every combination can be decomposed into this structure here. So basically the structure is an open parentheses plus x plus closed parentheses plus y. And so from this, what we can find is that basically the length of, let's call this s for example, the length of s is which is pretty much just 2n, because n is the number of open and closed parentheses. So if n equal to 3, then the length should be 6, is 2, and 2 is just for the open parentheses and the closed parentheses, plus the length of x plus the length of y. And so this here is equal to 2n, right? So this here is equal to 2n because that's the length of s. So from this we can deduce that the length of x plus the length of y is equal to 2n minus 2. And with this, let's suppose that the length of x is some I. It can be I equal to 0. It's like basically let's suppose that x is the subproblem for I, which means the length is 2i. And so what would happen in that case, so suppose x has I pairs. So that may be like 0 or 1 or 2. So 0 in this case when it's empty, and this case it's 1, for example. And so let's think about, so this means that the length of x is 2i. So what does this mean for the length of y? If the length of x is 2i, that means the length of y is whatever is left. So the length of y is basically whatever is left, which is 2n minus 2 minus the length of x, which is 2i, which means this here is 2n minus I minus 1. So we know that y has n minus I minus 1 pairs, right? So with this, we know the subproblems that we have to solve. We have to solve this subproblem for n minus I minus 1, and we have the subproblem for I, right? One with I pairs and one with n minus I pairs. So from this, we can solve our problem using recursion, but instead of recursing using the number of open and closed parentheses, here we will recurse using the number of pairs that are left to add, so that we can have the final string that is correctly formed. So what would that recursion look like? So what we need is we need to try all of them, right? We need to try all the possible I. So basically try I equal to empty, so that we can have something like this one, and then try all the possible y's, and so basically try all the possible values of I. So that means we will do 4, so this would be our pseudocode. So what we will do is we'll try all i's, so that would mean in the range of n, and we will go through all possible x and y, and form the strings or the valid parentheses expressions using this here. And so that means here we would do for x in, we will call the same function, which is, I'm just going to abbreviate it by generate for I. Let's call this function generate for n. And then we will go through all possible y's, which we said it's pairs of n minus I minus 1. And so in generate for n minus I minus 1. And the formula is we will add to our result, which is the final array that we need to return. We will add using this formula here, which is having an open parentheses plus x plus a closed parentheses plus y, right? And we'll go through all of them, so we will be trying all the combinations, and we will return result. And this would work and not have duplicates because we are going through all the possible I values only once. And so we'll try this one where x is empty, and then we'll try this one where y also is decomposed into x empty and then y value here, and then we'll try this one where x is empty and then y is decomposed as as another one where x is this one of length 1 and y is empty. And so using the recursion, it will keep decomposing, and because we are guaranteeing the valid parentheses expression, because we are ourselves adding these open and closed parentheses and they are added nowhere else, we guarantee that it's well formed. And because we are going through them in order, I equal to 1, I equal to 2, we will get we will not get duplicates. Yeah, so that's the recursive solution. So let's code it up and see if it passes. Okay, so now let's code the solution that we just went through in the concept explanation. So what we need is we need to have a result array to put the result, and then we just go through I in order, and then we enumerate all possible x's, and that would be generate parentheses. It was called generate in the explanation, and here of length I, because those are the number of pairs, and same thing for generating y's, and those are of length n minus I minus 1. So that's the length of the number of pairs we should have, and then we append with open parentheses plus x plus close parentheses plus y. And then at the end we return res. We just need to handle the case where n equal to 0, where we need to return just an empty one with an empty string. We shouldn't return just an empty one for n equal to 0. And that's pretty much all there is to it. So let's submit. Okay, so that solution passes. And there is a slight optimization we can do here, because you can see generate parentheses here. Maybe we call this one with 2, and then in another pass, this one has like this value is 2, and so we will be doing the same computation multiple times. So that right away hints to us that we should use memoization for this, and then just if we had calculated a solution, store it so that next time we call the same function, we don't need to do the computation again, and we can just reuse the previous result. And so that would mean here we would have this memo table, and we will check so we'll check here if the result is already calculated. We'll just return the value, and we need to store it when we calculate it, which means here we will need to say that memo of n is equal to res. But to have that working, because here it will be reinitialized because it's the same function, so I'm just going to define a helper function that will help this be easier to do. And so it would be like this, and we will be returning memo for n, and here we'll be calling helper for n, and we'll be initializing the memo array externally. And basically what changed here is just before returning the result, we just save the value in a cache here, which is this memo table, and then if it's already computed, we just return the value. And here I need to call helper instead, because that's now the function that is used. And that's pretty much it. Okay, so that solution passes. And now whenever we have a solution that uses recursion, and then we can optimize it to use recursion with memoization, we can right away think about using dynamic programming to make it even faster. And so here, the only thing we need to change for the dynamic programming solution, we'll need to keep this because that's the core, and we need to keep this because that's what's doing the decomposition, right? The only thing that we'll need to adjust is this. Now, since I'm no longer going to rely on the recursion, I'm going to need to use a table here, right? And so let's call this let's get rid of this first and get rid of that. And I no longer need the helper function because it's going to be dp solution, so I need my dp array, and I no longer need this here. So this is just for the first case when n equal to 0, this empty string here. And now to go through all of them, instead of doing the recursion, I will go through the range of n here and compute all the previous state. And so to compute all the previous state, this has to stop at j. So first it will compute the state for n equal to 0, n equal to 1, n equal to 2, so that next time we go to the subproblems here, I would have already computed these states. And so that would mean here I will need to just get it from the table, because I know I already computed it, because I've already passed through the first state beforehand using this for j loop. So this would be dp of n minus I minus 1, and that pretty much should do it. except here it's no longer n, because now we are doing it for this j. So this is to get all the way until n. I need to have it n plus 1, and there is no need to go through 0 because we already set it up here. So I can start from 1, and here it's j minus I minus 1. And that's pretty much it. And no need to do a helper here, since the value would be at the end will be stored at n. That's the last state that we computed, where it will contain all of them. And what should I add here to the DP? I should add the result of the substate, right? Which means here I should append the result, and the result I should initialize it here, because basically for j equal to 1, I'm computing all the pairs for n equal to 1. And then after that, for j equal to 2, I'm computing all the pairs for all the pairs that are equal to 2. And so for each one of them, I'm doing that I'm putting that in this res, and then at the end I put it in the DP array and reuse these in here with these subproblems. So let's run this, and that looks good. Okay, so that solution also passes. So the only thing I changed pretty much is this, in computing all the states before, needing them so that I don't need to do the recursion, and I can just use the table that I organized my iteration in a way that I'm sure that I already computed them, and at the end I just return the result, the final result for n. So yeah, that's pretty much it for this problem. Thanks for watching, and see you next time. Bye.